Alright guys, so before we start today's lesson, we're going to look at problem number 7 from 2.1's assignment. Now this one here, it wants us, I believe, to find the other 6 trigonometric or other 5 trigonometric functions. And they gave us that secant of x is negative 5/2, and tangent is less than 0. And really for any of these here, it's going to be helpful to really go back to the triangle, because we can do this in many different ways. And we've seen different ways to do this. But I think the easiest way for us to look at this is just make the triangle on the graph. And it works every single time. So this here is I've found the best way, or kind of easiest way, to actually look at these. Now, secant, we know is the same as 1 over cosine. So that also means that cosine of x is going to be negative 2/5. So secant's 1 over cosine, so really we can flip the fraction and find out what cosine is. Now we're told that cosine is negative 2/5, and tangent is less than 0, so tangent's negative. Well, cosine is negative in only 2 spots. It's negative in the second and third quadrant, because cosine adjacent, yep. And the only place where cosine and tangent are both negative is going to be in quadrant 2, because tangent's negative in the second and third. It's positive in the first, or second and fourth. It's positive in the first and third. So what that's telling us is that our triangle is going to be over here. Questions on this so far? Now, cosine is adjacent over the hypotenuse. So we have 2 and 5. And the 2 is going to have to be the negative one. Because, again, when we went over this with the coordinate plane, we're on the negative x-axis, positive y, and the hypotenuse is always going to be positive. So that's the negative 1. Now, to find the other side, we can just use Pythagorean's theorem, saying that 2 squared plus b squared is equal to 5 squared. But really, we're just saying b is equal to the square root of 5 squared minus 2 squared. Well, 5 squared is 25, 2 squared is 4. So we're saying b is the square root of 21. Now, I leave it as the square root of 21 because it doesn't simplify from there. That's as simplified as it gets without turning it into a decimal. So square root of 21. And now that we have this, we can really find the rest. Sine of x is going to be opposite over the hypotenuse. So square root 21 over 5. Tangent of x is opposite over adjacent. So negative square root of 21 over 2. I put the negative on top because just how I normally set these up, I don't like leaving the negative in the bottom of a fraction. That's just me. So we have sine, cosine, tangent. We already have secant, but we still need cosecant. Well, cosecant's going to be 1 over sine, so we can flip sine, which is 5 over the square root of 21. But we still have to rationalize the denominator, and luckily for us, the yellow calculator will do it for us. We don't have to work this one out if we don't want to, but it's going to work out to be 5 squared root of 21 over 21, because essentially we're multiplying top and bottom by the square root of 21, and there's no common factor to simplify. And the last one we have is cotangent of x, which is going to be negative 2 over the square root of 21. When we rationalize it, we get negative 2 square root of 21 over 21. And that's it there. Any questions over any of this here? Does this make a little more sense now? And I think even when we start solving these, and most of these here really don't show up on the ACT, and if they do, they show up as one question out of 60. And this, again, that's part of the reason why we don't put a big emphasis on these, especially for those that took the ACT prep class, because really studying and understanding a lot of the trigonometric problems that show up on there are helpful if you're aiming to get a 36. If you're trying to get a perfect score, then you focus on those last few. And we focus more on the others because they show up more than one or two questions. And these here always show up in the 50 to 60 range. If they're going to show up, they show up between problems 50 and 60. Now, if there aren't any other questions, are there any other questions on the assignment? Well, assignment, because we only had one. Now, what we're doing for the rest, or this lesson here, 2-3, is solving. We're solving these trigonometric equations. And the way that we solve these, we can use a lot of what we've already done. The ways that we solve quadratics and the methods that we use to solve quadratics in Algebra 2 still work for these here. Because if we look at this here, we have sine of x plus the square root of 2 equals negative sine of x. So you don't have to write this down. I'm going to reset it in a little way. First, if I said that we had x plus the square root of 2 is equal to negative x. If we were solving this one here, what would we do first? Or what would y'all do first? X plus the square root of 2 equals negative x. Right, I would subtract the x from both sides. We're trying to get the x's by itself, yes? I mean, we could have added x and then subtracted the square root of 2. Either one works. Because what that tells us is we have negative 2x equals the square root of 2, yes? Then what would we do next? Divide both sides by negative 2, telling us that x is equal to negative square root of 2 over 2, yes? So when we look at this here, we can do essentially the exact same thing. Because I'm going to rewrite it. Because the first thing I can do is subtract sine of x from both sides. And what that'll tell us is that the square root of 2 is equal to negative 2 sine of x. I just didn't flip it like I did on the first one, but it's the same thing, yes? We're one short. Okay. No. Was hoping, but here it is. Yes. Maybe this right here. Any questions on this so far? Because we're good with negative sine of x minus sine of x. Then our next step would be 2. Again, we're trying to solve, so we would divide both sides by negative 2, which is really telling us that sine of x is equal to negative square root 2 over 2. Now, there's two different methods that we can use from here. And one of them is applying sine inverse, because we can apply sine inverse to both sides. and have x is equal to sine inverse of negative square root 2 over 2. But really we're saying sine of whatever this angle is gives us a value of negative square root 2 over 2, yes? Square root 2 over 2 should seem like a familiar value, yes? It's off the unit circle, isn't it? And Johnny, I'm going to get you a unit circle. So here on the unit circle, we have different points going all the way around, yes? And the x value is our cosine, the y value is our sine, yes? So I can actually just pull this up and look and see where sine is, what angle sine would be negative square root 2 over 2. So if I look at all the y values, well, it shows up at (5 pi over 4). Because at 5 pi over 4, we have a y value of negative square root 2 over 2, yes? And if I keep going around, well, we also have a value at 7 pi over 4, yes? Can I keep going? Because I know that our unit circle only goes between 0 and 360, doesn't it? But if I wanted to, I could add 2 pi to 5 pi over 4, yes? And that would still give me the same angle. Because we know with sine and cosine, they are cyclic functions, they repeat themselves. So I could add 2 pi to both of these, yes? And I would still get a value of negative square root 2 over 2. Well, I could add 4 pi instead of 2 pi, yes? And we'd still get the same answer, yes? Because we could keep adding 2 pi, keep going around the unit circle and still getting that answer. So 2 pi n for any value of n. Because what that's saying, 2 pi n, is really saying that every time I go around the unit circle, a distance of 2 pi, we get back to the same answer. And we have to add this because did they restrict the values of x? Did they restrict the values of our angle? Well, no. So 7 or 5 pi over 4 does work. Because our starting equation, because we're saying that sine of x is negative square root 2 over 2. So I'm making sure that it is, well, I have to change it to radians. And our answer we're looking at is negative alpha y equals enter, second square root 2 over 2. So I'm putting this up here so we know what the decimal value is, because unfortunately the graphing calculator gives it as a decimal, not as a radical, or in simplest radical form. So if we said sine of 5 pi over 4, we do get the negative square root 2 over 2. So 5 pi over 4, if I said sine of negative alpha y equals enter 3 pi over 4, essentially I subtracted 2 pi from it. Let's see what we get. We get the same value. So I could take this here and we can say plus 2 pi. I get that same answer. Or we can do 64 pi. So we've gone around the circle 32 times. We still put the same answer, yes? Because they didn't restrict what the angle could be, any of these work, positive or negative. So we have to add the 2 pi in, essentially saying anytime we go around the circle, this works. Now there are some cases where we don't necessarily have to say 2 pi in, And that's if the two angles are 180 degrees across from each other. So if we looked at, say, pi over 4 and 5 pi over 4, because on the unit circle, those are 180 across from each other, we could just say pi n, because one would get to the other. They just go back and forth. But otherwise, we can just say 2 pi n, and that'll cover it. Questions on these here? Cosine of x minus the square root of 2 equals negative cosine of x. Well, again, we can do the exact same thing we just did. We can subtract cosine of x from both sides, which will tell us that negative square root of 2 is equal to negative 2 cosine of x. Well, then the next thing we can do is divide both sides by negative 2, telling us that cosine of x is equal to square root of 2 over 2. And again, if we look at the unit circle, because the unit circle, especially with these, is going to be helpful for us to get all the different angles that we could possibly have for cosine. So we're looking at the x values. Well, one of them is pi over 4. Now again, because we are not restricted on what our angles have to be, we're going to add 2 pi n to it. Now for the other one, if we keep going around, well, we do get a positive square root 2 over 2. It's 7 pi over 4. Plus 2 pi n. And those are the only two multiple angle spots where we have square root 2 over 2. So that would be our answer. Questions on these? For here, because we have our negative and a negative on this side. On the other side, we have negative and negative. Yeah. No. It's a good time to check in and make sure, because it's very easy. I do the same thing if I'm not paying attention. I'll drop a negative somewhere, and then it goes completely crazy. Any other questions? Now, I think it is good to look at the unit circle, because just taking cosine inverse of square root 2 over 2 would work, but it would only give us pi over 4, or our 45 degrees. It wouldn't give us the other angle, because if we remember back to our last chapter, cosine inverse function only works, so we had to restrict the range, or our values of the angle, between 0 and pi. So it only would give us those values out. It would only give us one value. It wouldn't give us both. So it's sometimes good, especially to look at the unit circle, if it gives us values on it. All right. Tangent squared. Now these here, I mean, there's different ways we could go about looking at this. 3 tangent squared of x minus 1. If they were both perfect squares, because tangent squared is a perfect square, but if we had, say, 4 tangent squared minus 1, it would be a difference of perfect squares. We could factor it and go about it that way. But again, that's the same thing we did with quadratics for solving. Another method we did with quadratics like this here, so if I said 3 x squared minus 1 is equal to 0, because we could solve this by completing the square, or factoring if we could factor it, or the square root method. If we remember, the square root method is to get the variable that's being squared by itself, and then take the square root of both sides. And the square root method works very well if we don't have a term to the first power. Here we don't, so we could use the square root method, which would mean we would add 1 to both sides, telling us that we have 3x squared is equal to 1. And then we could divide by 3, telling us that x squared is equal to 1/3. And now that we have the square root by itself, we can, or x squared by itself, we could square root both sides. And again, whenever we take the square root of both sides, we have to add the plus or minus. We have to add the plus or minus. In the square root of 1/3, well, the square root of 1 on top is just 1. But we can't take the square root of 3. And if we rationalize this, we get the square root of 3 over 3, plus or minus the square root of 3 over 3. Questions on this so far? We can essentially do the exact same thing with tangent. And actually what we've just done essentially is just use substitution again, because we talked about that months ago. We talked about that in August, where we can substitute in u for one of the parts to make it easier to solve. Essentially that's what we did. But instead of using u, we used x. Because we would do the same thing here. We would add 1 to both sides, telling us that 3 tangent squared of x is equal to 1. Then we would divide both sides by 3, telling us that tangent squared of x is equal to 1/3. And last but not least, we would square root both sides, telling us that tangent of x is equal to plus or minus, well, 1 over square root of 3, which is really telling us that tangent of x is equal to plus or minus square root 3 over 3. Any questions on this here so far? Okay. I'm drawing this out so we can kind of see it. You don't have to draw it out because we have unit circle, yes? And on the unit circle, tangent was neither placed on it, because all the points going around the unit circle were sine and cosine. Well, really, it was cosine comma sine. It didn't have tangent, yes? But luckily, we did provide a little space at the bottom that told us when tangent was square root 3 over 3, yes? And that was at pi over 6. Or 30 degrees, yes? Do y'all remember what the reference angle for quadrant 2, 30 degrees was? Or pi over 6 is going to be when this angle is pi over 6, yes? Or we could use the fact that sine and cosine will be the same values but different signs, which is over here at pi over 6, yes? And again, we can really manipulate the angles, because 180 degrees is the same as pi, yes? Or 1. 1 minus 1/6 is 5/6, yes? So what's 1 plus 1/6? Well, we'll have 6, because we'll be down here. Seven pi over 6. And here we'll have 11 pi over 6. Because 11, 12, 1 less than 12. 12/6 is 2. So it's really manipulating these fractions. Now at this point you're saying, well, on the first two we only had two different kind of unique angles, yes? Here we have 4. Because here at pi over 6, tangent is square root 3 over 3. At 7 pi over 6, the value is square root 3 over 3, yes? Now at the other two, it's negative square root 3 over 3. And at 11 pi over 6, it's negative square root 3 over 3. But we said tangent of x is equal to what? Plus or minus square root 3 over 3. So we actually do have these 4 values. So what we could say is that the answer for this here is that x is equal to pi over 6 plus 2 pi n. X is equal to, I'm going to order these, it's going to seem a little weird, but it'll make sense here in a minute. 7 pi over 6 plus 2 pi n. X is equal to 5 pi over 6 plus 2 pi n, and x is equal to 11 pi over 6 plus 2 pi n. And again, I ordered these in a specific reason to kind of show a point. Now the first two I put down was pi over 6 and 7 pi over 6, yes? What is the distance between, or our angle, between pi over 6 and 7 pi over 6? What is this value here? What is that angle? 1 pi, yes? So if I added pi to pi over 6, I would get 7 pi over 6, yes? And if I added pi to 7 pi over 6, I would get the equivalent of pi over 6, yes? Because we would be switching between these two here, yes? And if we have this flip and both of these work, I don't have to write these two statements here. Because if those two angles are 180 degrees apart from each other, we can make this 1. Because I could say pi over 6 plus, how would I change the 2 pi in? It's just pi in. Because each time I added pi to pi over 6, I got the 7 pi over 6. And back and forth, because they're switching 180. So I could take those two and make it into 1. Well, and the same thing true for these two here. So we could say this is x is equal to 5 pi over 6 plus pi n. When we have that two of the answers are 180 degrees apart from each other, and we don't have the restriction on what the angles can be, we could rewrite it as these two here. And having the 4 above it listed is not wrong. Those are the correct answers. These two here are just a simpler way to write it. Now, with the first two, we couldn't write it that way because those were not pi apart. So it would have been harder to rewrite it as a single expression with them being not 180 degrees or pi units apart from each other. But since these are, we can simplify to this here. Now, if you write the 4 out, that's fine. That is the correct answer. But if you remember and notice that they are 180 degrees apart, you can simplify it to just the 2. Also wanted to point this out just in case you do look at the back or checking your answers and see only 2 answers, or you got 4, this is why. Questions on these here? Let's look at this one here. So if I was solving this, what's the first thing we can do? Well, we want to get sine by itself, yes? Because, I mean, we could use the Pythagorean identity to rewrite sine as 1 minus cosine squared. But is that really helping us? No, it's making things a little bit more challenging. Because we can add 3 to both sides, which will tell us that 4 sine squared of x is equal to 3. What would we do next? Divide both sides by 4. Any questions on how we got to sine squared is equal to 3/4? Is 3/4 one of the values on the unit circle? No, it doesn't look like one of those, does it? And again, when I was looking at this here, this seems a little weird. Why did they pick this? Or why are we doing this one here? Because even if I thought it was weird, I still put it on here. So let's go on and do the last step. Our last step is to what? Square root both sides. Square root of sine squared is just going to be sine of x. Equals plus or minus, because we square root both sides, we do need the plus or minus. And if we look at the square root of 3/4, we can break it up into 2 parts. So we can take the square root of 3, which is just square root of 3, over the square root of 4. Well, what is the square root of 4? 2. Okay. Square root of 3 over 2 is on the unit circle. Yes? And again, I had to look back at it. And okay, when we square root, it does give us one on the unit circle. Now, since we do have the plus or minus, we actually have 4 values that show up on the unit circle. And since it's sine, it's a lot nicer, because it'll tell us directly what it is. We just have to look at the y value. So we're looking at positive or negative square root 3 over 2. So we have that x is pi over 3 plus 2 pi n. We also have that x is 2 pi over 3 plus 2 pi n. We also have that x is 4 pi over 3 plus 2 pi n. And lastly, x is 5 pi over 3. So those 4 there would be our answers, yes? Are we able to write these a little bit nicer? Well, yes. Because these first 2 here, pi over 3 and 4 pi over 3, are 1 unit apart from each other, 1 pi apart from each other. Because I can take 1 plus 3 and get 4 if we're adding a whole. So I could say that this is x is equal to, I wouldn't use 4, pi over 3 plus pi n. And here we can say x is equal to 2 pi over 3 plus pi n. And whenever we do the pi n, we always pick the smaller of the 2 angles to do it with, or apply it with. So there is nothing wrong with writing out all 4, because that is the correct answer. But if we wanted to simplify it down into just 2, we can use pi n instead. And again, we have this here because we don't have a restriction on what the angle is going to be. Now, when we start having restrictions, it's going to be something particular. It's going to be between 0 and 2 pi. 0 and 2 pi. We're going to restrict it to one time around the unit circle. And if we had that, then we would have our 4 answers without the 2 pi. 2 pi in. And that's it. Questions on this here? Now, I'm going to pull up the graphing calculator here. So we said we had 4 sine of x squared. What was it? Minus 3, wasn't it, for this one here? I'm going to hit graph. So we get this here, yes? And this is one way we can check our answers. So one of the answers that we had was pi over 3, yes? And I think I've gone over this with y'all. We can go second trace value. We're picking a value for x because unfortunately pi over 3 is not a nice number to especially find on a table. So we can go second pi divided by 3. So we gave it the x value, the y value is 0. Isn't that what we wanted it? We wanted this function to equal 0. So that is one of the correct answers. I can do it again. Second calculate value, we can say 2 pi divided by 3. I get a value of 0. Second trace value, 4 pi over 3. We get 0. And then our last one was 5 pi divided by 3. We get 0. So it's one way we can check our answers. And especially if y'all end up taking the ACT again where they're asking for where do 2 graphs intersect or cross, we can type them in or plug them in, graph them, and then just check the value, see which one works. But I just wanted to show you that there, because a lot of these here do get a little weird on the graphs themselves. But we're going to stop there for today.